pleasure for me to be able to introduce David Hughes. David is a professor at the University of Leeds in the north of England, and I would describe him as an applied mathematician who's specialized in fluid mechanics of all different kinds, but especially hydrodynamics, and also lots of problems in geophysical and environmental fluids as well. And today he's going to be talking about flux expulsion, boundary layers, and turbulence.
Thank you, Gavin. The introduction. Morning, everybody. This is what I'm going to talk about. As we know, it's always a challenge to make one talk fit in a meeting. This might be as close as it gets in the title. I think all the key words for that. Turbulent boundary layers. So it's not far off the theme of the meeting. And so what I'm going to try to do is to bring together work that I've done, different bits of work all on the same topic, with a whole bunch of people over a number of years. So these are the people. Stephen Griffiths is a colleague at Leeds. Julian Mack, who's now in Hong Kong, was a student with Stephen and me. Todor Kondich was a postdoc with Stephen and me, and Francis Poonam and Jonathan Tessier are at various places in Canada. Right. So let me, this being a tutorial, I'll try and tell you a little bit of obviously why we're interested in the problem and the history of the problem. In some sense, it's a very simple problem. Prasad yesterday said he was going to talk about stuff that was simple compared to plasma physics. This is, I would say, even simpler in some sense, you'll see. But it's a problem that has generated interest over 60 years. And the motivation is astrophysical. So this is a picture of the surface of the sun, a very high resolution picture of the sun from one of the most recent telescopes, one of one's in Hawaii. And these are convective cells. So each of these cells is about 1,000 kilometers across. So it's an amazingly high resolution picture. And you can see that it forms a sort of cellular structure. Fluid comes up in the middle, goes down at the edges. What they can also measure now is the magnetic field. So this is an equivalent picture, not at the same. I couldn't find it. It would be helpful if the people that published the magnetic picture also published the kind of convection picture like that at the same time, but they don't. So these are not at the same time, but they're at the same scale, if you like. And on this, which isn't a great projector, probably comes out better on that one. The bright stuff this is magnetic field intensity, and the bright lanes, the yellow and the red, are in the lanes of the convective cells. So one gets, even without understanding the convection problem, one gets the idea that there is fluid motion, fluid cellular motion, which pushes magnetic field to the edges. And that's what is called flux expulsion. And it leads one to think in general about the canonical problem if you've got a cellular flow, a vortex flow with a magnetic field, what happens? So another astrophysical motivation is this. I'll explain this picture in a minute. So I'm going to be interested in vortices and magnetic field. Where else might we get vortices or cellular motion? So convection is one possibility. It's quite a complicated problem. Another where you might well get vortices is through instabilities of shear flows. Yeah. So shear flows are in some sense ubiquitous in astrophysics. This is a a nice example of a shear flow. So this picture is the solar rotation, the internal solar rotation rate, measured through helioseismology. So just like on the Earth, we know what the Earth is made of, essentially through the properties of waves that travel through the Earth, generated through earthquakes. The sun is shaking all the time, gently, and sends sound waves throughout. And they can do amazing measurements, especially through satellites that can get very long time signals, uninterrupted time signals of solar oscillations. Now, to measure the solar rotation rate is a particularly sneaky measurement because you have to distinguish between waves going prograde and waves going retrograde, which they can do. And then it's an inversion problem. And the result of the inversion problem is this. So the rotation axis, of course, is this one. Red is fast and blue is slow. So it's been known for hundreds of years, since the time of the invention of the telescope, that the equator on the sun rotates faster than the poles. Okay, so the equator of the sun goes round in about 25 days. The polar regions go round in around 40 days. And people have known that through looking at surface features, like sunspots, for example. And it's been a theoretical question until recently. What does the sun's rotation rate look like inside? But now it's a theoretical question as to why it looks like it looks. But this is not theory. This is an observation, okay, through helioseismology, and was a surprising observation. Because what people used to say was, oh, well, it's rotating. If it's rotating, it'll be constant, aligned with the rotation rate, which is true if it's rotating quickly enough. But that's not what happens here. Okay, it's not constant rotation on cylinders. So what you find is if you go into the sun at the equator here, then there is very little change of rotation rate until you get to the bottom. Here, this is the bottom of the convection zone. So the sun has a convection zone from 70% straight to the surface and a radiative zone from 0.25 to 0.7. So this is the convection zone, and there's very little change in angular rotation, angular velocity. Then there is an abrupt slowing down from red to yellow. Conversely, if you come in at the poles, there's very little change, and then you speed up, unless you come in on this kind of magic latitude here, where you're at the same color all the way. So this region here, this white region, is called the tachypline. It's a region of intense shear in the sun, the bottom of the convection zone, above the radiative zone. And so it's potential, it's got potential for all sorts of things, one of which is shear flow instabilities, which lead to vortices. So that's another reason why we might be interested in vortices and magnetic field. It's believed there is a strong magnetic field down here. Of course, the sun has a strong magnetic field, but reasons I'm not going to go into, it believe that it's quite strong in fact. Okay, so that's some sort of general motivation for why we might be interested in vortices and magnetic field. Yes, please.
So the color is the rotation rate, right?
Yeah.
It's always the same direction, just different magnetic. But like rate.
Yes, it's all in the same. It's all rotating. And
Same direction.
yeah,
It's just different.
and that's right.
And what's white?
So the white, that's right. So the white is this famous tachypline. So the white is not part of the color scheme. The white, this came from the cover of the book, the tachypline, so we had to mark the tachypline. Yeah, but that's right. The white is not part of the color scheme. The white is this thin region of shear. It's not quite known how thin it is, because that's very hard to resolve. It's known it can't be thicker than a few percent. It could be thinner. Yeah, so the white is this strong, where there's a reason. Well, you can mention let me say a little bit more. So the tachycline has both angular velocity gradient in radius, right? We go from red to yellow with radius, but also in latitude. Right. Right, so I'm just going to leap ahead to show you a picture. I'm going to come back to this picture. So you don't need to bother too much about the details of this picture. But I thought it was a good idea to put it in now so that if you think where the heck's he going, this will try and answer the question of where I'm going. Okay. So without going into the details of where he came from, this is a vortex. Okay, I'll say more later where it came from, but this is contours of vorticity. So you can just think of it as a isolated vortex. Okay. And the top, this M, which again I will explain later, it's some measure of magnetic field strength. But the top one you can consider there to be no magnetic field. So it's a vortex and it sits there. And that's that. Okay, it might be K, but that is that. The middle one has an extremely weak, large-scale magnetic field. What happens, of course, well, say of course, what happens is that the vortex winds up the magnetic field, but nothing much happens to the vortex here. Okay, but the magnetic field in the middle is entirely passive. It gets moved around by the vortex, but it has no dynamical consequence. The interesting one is the bottom plot. Now, the bottom plot, the magnetic field, is still extremely weak in a way that I will quantify later. But the reasons which this whole talk is about, it leads to disruption and even almost destruction of the vortex. Okay. So that, looking ahead, is kind of what we're trying to explain. The effects of the significant effect of ostensibly very weak magnetic fields on vortex coherence. Yeah, so the field is transverse to the field, transverse to the vortex. In what? Let's call it the X direction. Yeah.
The vortex is in a plate which is directly in charge or not.
Absolutely. Yes. So I'll explain all the details. But yes, yeah. If you just bear with me a bit, and if it's not clear, come back. So this was just, as I said, don't get. I hope to explain this picture properly, but this was just to give you an idea of what we're going to be talking about. Vortex disruption by magnetic fields. Right, so hopefully this will answer your question. So this is everything I'm going to be talking about is MHD. Okay, classical single fluid MHD. I don't think you really need reminding, but I'll remind you nonetheless. So magnetic field is governed by the induction equation. Solenoidal, of course. I'm going to assume the flow is incompressible. And we just have the standard momentum equation with the Lorentz force. Right. So it's standard MHD. Even more, it's going to be 2D MHD. Okay, so really these are going to be the equations that I'm going to be dealing with. Probably worth just pointing out the notation because what we call psi, you guys don't call psi, what we call A, I think you call psi. Loads of room for confusion. So it's 2D. So we have a stream function, which I'll call psi, and a flux function, which I will call A. And the induction equation, of course, becomes very simple in a 2D case. It becomes the heat equation. It becomes the equation for a passive scalar. Okay. This is now the induction equation. This is uncurling the induction equation. And this J psi A is the Jacobian. It's the nonlinear term. It's the effective term. And it's useful in 2D, as in many 2D fluids problems, to work with vorticity rather than the velocity or anything. Gets with the pressure, always a good thing. So we have a vorticity equation. This is the effective term vorticity, and this is the Lorentz force. Okay, the Lorentz force is the Jacobian of A and del squared A. It has psi and omega in it, so omega is the vorticity, and you have to invert. They're related. Omega is minus del squared. So there's two equations and an inversion, if you like, and three-dimensionless parameters. For the purposes of this talk, two of them are going to be absolutely crucial. One of them less. So the parameters are the standard Reynolds number, the magnetic Reynolds number, like the Reynolds number with the magnetic diffusion underneath, and this quantity, okay, m, what I'll call m squared. This is going to be critical to everything that I'm going to be talking about. So m squared is, various ways you could think about it, is the ratio of the alphane speed squared to the fluid velocity squared. It's the ratio of magnetic energy to kinetic energy. Probably a good way of thinking about it. So I'm going to have in mind a problem where I have a vortex with a kinetic energy and a magnetic field imposed upon it, which has magnetic energy. And m squared will be the ratio of the energy in the magnetic field to the square. No, sorry. M squared will be the ratio of the magnetic energy in this imposed field to the kinetic energy in the flow.
What kind of 2D is that? This is thin layer 2D, right? It's not strong magnetic field.
No, sorry, yeah, good point. Okay. So this is 2D in the plane. So everything is, so the field is in the XY plane, the flow is in the XY plane. Okay, so there's no Z dependence. Everything is in the XY plane and dependent on X and Y and T. Okay, and another thing which is worth pointing out is that astrophysically, which is at the heart of what I'm going to say, astrophysically, RM is huge. Almost everywhere, RM is huge. So typical numbers for the solar convection zone, people will bandy about are like 10 to the 10. You know, they're so big, not quite clear how big they are, but they're big. So RM is extremely large astrophysically, and that we'll see is important. All right, everyone happy? Okay, let me come back. So within this problem, or within any sort of MHP problem, there's two problems one could look at. One could look at a kinematic problem. So a kinematic problem means here's the flow given. Let's work out what the field does under that flow. And the field doesn't change the flow by assumption. So that comes down to solving this equation, just this equation. Okay. Then, of course, there's the dynamic problem, which couples the field through the Lorentz force back into the flow problem, the vorticity equation. Everything, that vortex disruption that I showed you is obviously dynamic. Field is having a dynamic effect. So we want to get to the dynamical problem. But to get to the dynamical problem, there are important aspects to the kinematic problem that we need to understand. And the kinematic problem, although incredibly simple to state, actually is quite interesting of itself. It's interesting historically. So I'm going to say a little bit about the kinematic problem. So by the kinematic problem, I mean psi is given, right? It might emerge from an instability, whatever, or you might just write it down, but it's just taken, right? The field has no effect on it. And then we work out what the field is. I'm sorry. J is the Jacobian of J of F and F by the X by times X. Possibly the other way around. Give or take a sign. That's what the Jacobian. So it's people might see it written in the sort of bracket almost or whatever, right? Various ways you can write it. It's the advective term. It's the non-linear. So here, it's the curl, the z component of the curl of u dot gradient. And this is the z component of the curl of the dot theta. Right. Right, from history. This is an old plot. On this projector it looks even older. It doesn't look too bad on it. So this is there are a few classic papers on kinematic flux expulsion. This is one of them by Nigel Weiss in 1966. This is an amazing calculation. I think this is a computation. And if you think, all you youngsters, if you think what people could do on a computer in 1966, this is an amazing calculation. So it's 2D, okay, but it's and what it is the kinematic problem. So it's the flow is given, and here the flow is some cellular flow which fills the box. In the field, why not? And these are just what happens at various times. So you can see that the field, these are field lines. Of course, graphics in 1966 was not as snazzy as it is now, but these are the field lines. But you can see, at least on that one, you can see they're wound up and then they reconnect until there is no field left at the bottom. So this is called flux expulsion. We're going to need to understand this to understand the dynamical consequences of this kinematic. And Weiss looked at a variety of different flows. I put this up because if I have time, I'll talk a little bit about the dynamical consequences of these sorts of flows. So he looked at an array of eddies. He looked at side-by-side eddies, if you like. 2x2 eddies. Right, but this is the problem that he was doing. You solve one equation, the field is assumed to be so weak it has no dynamical consequences. Study the magnetic induction equation in isolation with velocity. And there's this is a problem that has attracted a few giants of the subject. So there's some important papers. Being Parker in '63 did something on this. Nigel Weiss. Keith Moffat, I'll come to this paper in a bit, and Rhymes and Young also address this. Okay, so even though you think, well, it's a very simple problem. Here's a flow. You put a field in. What happens? It's not. It does have some subtleties, and indeed did have some controversy at some stage. So what we do know, and what would have been known way before these papers, is what happens at the end. Okay, so what happens at the end? It's got to A has got to go to a constant. The magnetic field has got to go to 0. Okay. This is a famous theorem. Franklin-Batchelor theorem, Franklin 1974, rediscovered by Batchelor. in 1956 in volume 1 of Journal of Fluid Mechanics. And it's a nice argument. Say, if you have no diffusion, you get rid of the diffusion term, and you're steady, then you only have J of psi and A equals 0, so A has to be a function of psi. Then you say, okay, suppose I've got a little bit of diffusion, and I integrate round a closed contour. So this is just taking the equation, steady induction equation, two terms. This is using the divergence theorem in 2D, and this becomes 0 because I'm integrating around a contour, a streamline, sorry, a streamline. So U dot M, by definition, M is normal. Zero. Then you rewrite this in another way, use the divergence. Then the sneaky bit comes by saying this term is almost, A is almost a function of psi, because if eta, the magnetic diffusion, was 0, A would be a function of psi. Now, almost a function of psi. So I can write this as, I can move to psi being according. If I use the chain rule, this term, this in some sense should have been inside the bracket, inside the interval, it's the A by D psi. But it's on one streamline, so I can lift it outside. This becomes the integral of the flow around the streamline, which obviously is non-zero. So hence this term has to be 0 across streamlines. A has to be 0 across streamlines. So the final state is known from Prandtl-Batchelor theorem. Prandtl-Batchelor theorem applied to vorticity, which is a more complicated problem, but it's the same point. The non-linearity of the vorticity equation doesn't really come into this answer. That's only I have another relation. So it applies to this. So the final state is known, but what is not known is how does it get to this final state? And that was where the interest is. How quickly does it take to get there in particular? What are the key time scales in this kinematic flux expulsion? So this is from Weiss's paper again. So this is what flux expulsion looks like. This is magnetic energy versus time. It goes up, push the field to the side, it starts reconnecting, the field strength goes down, and it settles at a steady value. Okay. The flow is given all the time. The flow is not decaying. It reaches a steady state for MHD. These are various measures which we don't need to concern ourselves with, except this. I'll tell you what this one is. So one of these is the yes, it's A. One of these is the peak magnetic energy. Okay, peak magnetic energy and Weiss's numerics came to this scaling. Okay, clearly there is a scaling. This is magnetic energy, measures of magnetic energy versus the magnetic Reynolds number. So there is a scaling for, let's say, the peak energy as a function of the Reynolds number. And the interest is, what is that power? And there's various ways you can get to this argument. And this is why there was some controversy about this in the 60s, 70s, 80s. There's two ways you can get to it, which give different answers. Let me explain that. So this is what Weiss did. Okay, he had the numerics, but he also had this argument. So he went back to the B equation rather than the A equation. And he said, let me ignore diffusion at the beginning. What happens? Well, obviously, I wind up field through the induction term, the effective term. Then you say, but at some stage, you're going to get small scales out of this. At some stage, diffusion is going to bite. And you balance those two terms and say that's when the field will have reached its peak value. So B perpendicular So you can consider B perpendicular to the eddy, parallel. You can, so the advection term doesn't increase with time, but just like in a linear shear flow, the parallel component increases linearly with time. Okay, so there's a gradual linear reduction in the key scale as 1 over time. And Weiss then said, well, let me balance the advective term, curl of U cross V, against the diffusion term. Now, you have to be careful what you're balancing here. So U is the scale, U is the given scale. It's a vortex, it's a cell. So that's got some size and some scale, big scale. And it's working on the imposed large scale field. So that's how big the left-hand side. But the right-hand side, of course, is all to do with the strong field on a small scale. You push this, you started generating stronger field on smaller scale. To be balancing essentially large scale stuff against small scale stuff, which combined with this argument for the length gives you this nice arrangement here that the strength of the wound up field, if you like, goes as Rn to the third times the large scale. And at this stage, you haven't pushed it all into boundary layers. Still a filling factor of 1, so the magnetic energy actually scales Rn to the third. So that number of Weiss, which he had as 0.59, should, in some sense, if the theory was exactly right, be 0.66. And this, okay, it is the ratio of the length scales. And as a consequence of this, the ratio of the time to get before the field starts reconnecting, according to this argument, combines Rn to the third. It's worth remembering that it's Rn. And it's worth just noting again how he did it. He took the induction equation and he said, I'm forgetting diffusion. I'm going to consider just what happens in the diffusionless world. And then I'm going to say, when does diffusion, when does the term that I've neglected, when can I no longer neglect the term that I've neglected? It's what we do all the time. So if you really want to pick up the 0.66 numerically, this is flux expulsion in its purest form, okay? Where you have an isolated eddy in a sea of nothingness. So this is the stream function here. So it's decaying exponentially. So it's just a swirling flow, and there is a peak velocity. The swirling flow peaks at this radius. Okay. And you can do the scalings, okay, and the scalings are amazingly good. They don't project amazingly well, but they are. This is the peak magnetic energy, and this is the time scale to maximum. And based on the last 4 points, I think the scale, this is 0.661, and this is 2. So this really shows this is as good as it gets. Okay, in terms of the theory. So what we'd like to know is where that. Well, we have Weiss's argument for where that came from. Let's see how else we might get it, and why it's happening. Okay, so what's happening in this amplification and flux expulsion and so on. Okay. So in some sense, you can get quite a long way even without considering eddies. So you have a linear shear flow, a shear flow in X depending on Y, and a field which is purely in Y to begin with, and varies with X. Okay, so you're shearing this field, and you can solve the problem exactly. You can solve it by going back to A, B, and you can solve it. you know, here's the equation, here's the solution for A. Two things to note. One, the wave, so initially at t equals naught, the wave vector of the solution is purely in the x dimension. But as time goes on, they tilt more and more. Okay. And it's this tilting of the wave vector, and increase of the wave vector, that enhances the diffusion. So the diffusion has this nice form. So if there were no flow, if alpha were naught, alpha is the shear flow. If alpha were naught, of course, it's a purely diffusive decay. But if in the shear flow at large times, this is what matters, this term. It's alpha squared t squared. Alpha squared t cubed. Sorry. So it's an enhanced diffusion. Okay. Not going on an ohmic time scale, it's going on a shorter time scale, which is R into the third. Now you can sort of do that. So you can do that exactly for that case. You think, well, what about in a circle? That's what I'm bothered about, circular flow. Well, you can't quite do it exactly. But you can reduce it, you know, this PD just in one variable. So you look for a solution of this. So you go to polar coordinates, you look for a solution of this form, right? Because this at time t equals naught is purely in the x or y direction, depending on whether I define theta equals naught to be. Okay. So you look for a solution of this form, right? The I theta times some unknown function of S and T, and you get a PDF in F. You could solve that. So of course, at large times, you've got a very rapidly varying phase here. So you're better pulling it out. And you get this nice-ish equation for G. So it's a diffusion equation. Right, and this is the classical diffusion term. But at large times, even though you can't really solve this analytically, this is the term that matters. It's t squared again. You get t squared again. And so you get a time scale for expulsion, which again looks like O to the third times S omega prime, 1 over S omega prime. Sorry, I keep changing notation. This is very clever. S is now radial in polar coordinates. 2D plane polar coordinates, S theta. Then omega here is not vorticity, but is angular velocity. What do you notice? So the key, well, two things to notice. One is that the time scale is O to the third. The other is that all the action is taking place where the angular velocity is maximized. Okay, that's the key feature here. Clearly, something different must happen at the center of the cell because omega prime vanishes at the center of the cell. There's a nice paper by Bassett and Gilbert, which deals with the asymptotics near the center of the cell. Okay. So what you'll notice, possibly, this, how did I get to, so you might think, okay, we had a B argument, we got to R into the third, we had an A argument, we got to R into the third, but they're different arguments in some sense. The B argument says, forget diffusion, work out what's happening, and then work out when you could no longer neglect the term that you neglect. What we do all the time in fluid. Now, whereas the A argument hasn't said that at all. The A argument dealt with the evolution from all times. So there's a classic book, Keith Moffat's book on dynamo theory. He applied the let's forget a term until we needed to balance it to the A equation. Now, interestingly, if you do that, you do not get theta. You do not get R into the half. And I don't I mean, well, I do and I do not understand exactly what's. So what? And then in a later paper, Moffat and Kamkar did essentially that kind of A analysis. And this is what Keith said in the paper. It's rather interesting. The normal procedure for neglecting a small term, in other words, neglect it, solve the equation, and then evaluate the neglected term to see when it comes in, it doesn't work for A, but it does work for B. So that, I still think, is an interesting and not fully answered question as to why that is. Right, better scoot along. So that the example of pure flux expulsion really, where you do get the 0.66 scaling, that you really have to have an isolated vortex effect. So you might say, well, what if I took another cellular flow? So here's a periodic flow, much loved by people in dynamo theory, used first by Limrod in 1972. It's a periodic array, but it's got a vortex here, got a nice cellular structure. It's also got stagnation points. What is the answer? So I was just playing around with this preparation for this talk. Oh no, now I've done. Oh no, I've really done something terrible. How did I do that? I pressed the wrong button. Okay. So that picture of Weiss that I showed you, where the field grows and kind of just flattens, is more interesting for this Roberts flow, because that's what it looks like at low Rm. This is, again, it's magnetic energy versus time. So at low Rm being like 1,000, it grows, wiggles a bit, and flattens. But you can see that there's obviously different things going on in this periodic cell, because at high Rm, which is 10 to the 5 here, or 10 to the 4.5 here, this second peak is going to win. So it's expelling, forming these boundaries, but then it's doing something again, which has to be due to the presence of the two time scales, one to do with the stagnation point. Okay, because this is the scaling, and okay, as drawn, it looks as if they're straight lines, but they're not. This is not a straight line. This is curving, and so there is no simple scaling like Rm to the gamma when we've got stagnation points in the flow as well. So that's okay, a bit of an aside. Right. So much for kinematics. Now let's get to the meat of the talk, which is dynamics. This is a picture that we've already seen, so I don't have to linger on it, but now it maybe makes a bit more sense. We've defined M, right? So M is the magnetic energy. M is the ratio of magnetic energy to kinetic energy. Key things, you can read these are small. These are small numbers. Even the biggest one is 0.05. So 0.05, 0.03, 0.04. So this, in some sense, is a very weak magnetic field. But, as we've just seen, you can amplify a weak magnetic field by a factor of Rn to the third to make it a strong field on a small scale. And obviously that is what is behind all of this. Okay. So here are the field lines. So in the top one, it's flux expulsion, just like we've been talking about. In the bottom one, it's flux expulsion with a few wiggles. And in the bottom one, it starts off as flux expulsion. And then obviously there is an instability. The instability destroys the vortex. And that's what we'd like to understand. Okay, so sorry, where does this come from? So these came from the instability of what's called a tangent, but it's like a shear layer. Okay. In shear flow instabilities, there are two canonical sorts of flow. One is a shear layer, which means that flow at infinity is not the same in the crudest possible sense. So like a Kelvin-Helmholtz instability, it's very dramatic shear layer, Hansch flow of a smooth shear layer. And the other is a jet, where the flow is the same, plus or minus limits. And so this canonical jets that people love to study for square jet, the Bickley jet, it leads to vortices. Here we kept the longer wavelength, so we've got vortex pairs. But it's the same picture. So this is the vorticity, which results from the instability of this flow. This is the magnetic field strength. It is weak, and the magnetic and the vortices are here intact and here destroyed. So it's a sort of generic feature. You might say you don't need. This is how we did it historically. We did shear flow, we did vortices. Having done that, we thought we don't need to do. You could just take a vortex and deal with it at higher resolution, which is what we've done here again. So this is like the isolated vortex I showed. So you have to be, one thing you have to be careful of is if you want to do periodic boxes, which are kind of nice, then you have to be careful that your vortex decays at the time of the boxes, otherwise you will get furious effect. So this is the same vortex with exponential decay. This is the field, the nicer picture. Which, yeah, you can kind of see here, it's the vortex, the vorticity. So again, these are very, very weak fields, but increasing in strength. So this is a rundown experiment. So this is a very, very simple configuration. You start with a vortex. High Reynolds number, it decays very, very slowly. High magnetic Reynolds number, 10 to the 4, or 1.5 times 10 to the 4. And you vary m, you increase m squared. Okay. And you can see that here, the field is so weak that the vortex is just doing its stuff. Here, it's disrupted, but there is still some of it left. Here, kind of sort of, there's a little bit of it left. And here, there's no chance. Okay. So what we would like, so they're kind of pretty pictures, but you would like a theory which quantifies the vortex disruption in terms of the parameters. So that's where we're heading. Okay, so what's going on? Okay, so back to the 2D equations that we've already looked at. And we're going to apply the standard approach of fluid mechanics, which is to ignore a term, work out consequences, and then work out when we shouldn't have ignored the term was ignored. And we're going to do it for the statistic equation. Okay. So we're going to set, so we know that the magnetic field will, if it were purely kinematic, we know that the magnetic field will just wind up to give this peak field looking like orange the bird. Okay. So we're going to balance, we're going to say, when does the Lorentz force bite? Okay. So we're going to balance the advection of vorticity with the Lorentz force. As a sort of delimiting line between kinematic and dynamic behavior. So the advection of vorticity, that's all large-scale stuff. Okay. It's a large-scale flow, a large-scale vorticity on a large scale. But these are all large-scale quantities. This Jacobian here is that. Now, the one you have to be careful about is the Lorentz force, curl of the Lorentz force. They're components of the curl, which in the equations look like this. Now, you might say, I know that the field is on a small scale. So all of these derivatives, d by the x, d by the y, del squared, they are all small scale. So this term should look like a squared over L to the fourth. Little L to the fourth, where little L is related to big L through the magnetic Reynolds number in a way that we just see it. And that is true. This term does scale like A squared over L to the 4. And this term, steady, also scales like A squared L to the 4. The difference between them does not scale as A squared over L to the 4, which is, of course, what you want. So this is not the best way of doing it. What you should do, of course, is to move into, because this is X and Y, but X and Y are not natural coordinates in a way. You've got this vortex. You really want to be field aligned and field perpendicular. Okay. So you really want to write your Jacobian in terms of curvilinear coordinates and take one of your coordinates to be field aligned, one of your coordinates to be perpendicular to the field. And it is true. Standard, but these H's are the scale factors in curvilinear coordinates. The key thing is that 1 over H1 divided by H is 1, scale 1 little l, but 1 over H2 given H2 scales as 1 over big L. The del squared does scale as A over L squared. But the Jacobian, each of them scales A squared over L cubed big L. Okay. And that's the crux of the matter. So these two terms are indeed do scale as A squared over little L to the 4th, but their difference does not. It's their difference that is the Lorentz force or the curve of Lorentz force. So this is the argument one should use, and that's the key scaling for the Lorentz force. So now we say, okay, we've got convection of vorticity and Lorentz force. And we know how big little L is because we're saying that it's in the kinematic regime. We are right on the boundary, kinematic and dynamic. So we can, where we need to, we can take kinematic gain. So we balance those two. We put everything in, and we get that this is M squared, twiddles little L over big L cubed, but we know what that is. Kinematic, 1 over Rm. And so this is the crux of the matter. The field dynamic effects matter when M squared Rm is order 1. That's why when I said at the beginning, it matters that Rm is enormous, because the more enormous Rm, the smaller the magnetic field that becomes dynamically significant. That's why Rm is huge. Tiny values of the large scale field still matter by the M squared Rm. So does it work? Yes, do right.
Very nice way you can talk about it. Now that you have found the end result, could you have guessed it in the beginning?
Yeah, in some sense, because as you know, there are lots of problems, but there are other problems where M squared Rm comes in play. So I could have guessed that it would be M squared times Rm to somehow.
Right, that's what it is. There is no way to know anything.
But the fact that it's 1 does come from this, which comes from all of that kinematics. So yes and no. So how would we quantify that? In those pictures we saw vortices, some of which were intact, some of which had a little bit stripped off them, some of which were a tiny bit left and some had gone. So how do we quantify that to check whether this theory makes any sense? So this is what is often used particularly in geophysical context. This quantity here, so-called Weiss parameter. This is a different Weiss. It's a very Weiss-intensive problem. This is it's used in oceanographic flows. Is a flow sort of strain dominated or vorticity dominated? So this W, normal strain squared and plus shear strain squared minus omega now is back to vorticity. Sorry, but notation minus the vorticity square. So if W is very negative, you say it's vorticity dominated. And then you have to say, what do you mean by very dominated? Or very negative, sorry. Well, then of course you've got a choice. What is often used in the literature, we found, is that this is often taken as a criterion. It is, of course, arbitrary. It's been used. We took it, which is to say W is less than minus 0.2 times the standard deviation of W. Then we'll call it a vortex. Right? You could obviously change that threshold. Having got your Akubo-Weiss parameter, how do you define disruption? So how we define disruption, we define a disruption parameter, which is 1 minus the integral of this Akubo-Weiss parameter over the vortex. I have to be a bit careful what you mean by that. I'll come to that. Over the vortex divided by the Akubo-Weiss parameter over the hydro vortex. So if you're purely hydro, obviously this is 0. There is no disruption. And at the other extreme, when delta T is 1, then you've got full disruption. So we've got this parameter. So we've got a Akubo-Weiss parameter and a disruption parameter. So we're going to look at the disruption parameter calculated by the Akubo-Weiss parameter to work out whether that m squared Rm twiddle order 1 hangs together. Okay, so this is what Akubo-Weiss looks like. So what, you know, if I were to work this out, to plot this for the isolated vortex, this is what it looks like. Okay, so this is just W, not W less than anything, just W. Okay, and it does a good job. The dark stuff is the vortex. Where you have to be a bit careful when you do it is that you might get strong bits of vorticity that fly off. And you don't want those in your disruption because you disrupt it. So you have to kind of also have an algorithm for keeping track of the bit of vorticity that was connected to the vortex that you started with. Right, so this is Akubo-Weiss for the shear flow vortices. So this shows exactly what we do. So here's a vortex, and this is W. So this is 3 cases. No, 1, 2, 3. The left column is just W. So you just take your flow and you work out that W. And it'll be positive in places, it'll be negative in places. Where it's negative, it's vorticity dominated. Okay, so blue is negative vorticity dominant. Okay. Then you apply the W less than minus 0.2 sigma, which is the middle row. Okay. But that, you can see that it's picking up these strong bits, which it's spewed out. Well, I don't want those because they are clearly elements of the disruption. They still happen to be strong, but they've flown off somewhere. So then you have to do a further refinement to work out who's connected to the initial vortex. And so that's this one. So this is what we would use in that 1 minus the integral W to work out that disruption parameter. Okay. And these are the results. Okay, so I have results for both the shear flow vortices and the isolated. And our claim, remember, our claim was that disruption occurs if m squared Rm is order 1. So obviously what you should plot is disruption parameter. And this is disruption parameter at a certain time versus m squared Rm. And for the shear layer and for the big theta. I would say of course I would say that, but it's pretty good, right? So I don't know how well you can read all this. So the disruption parameter goes from 0 to 1. And m squared Rm here goes from 0 to 5. Then you can see that, so if m squared Rm is small enough, of course there will be no disruption. purely kinematic, m squared is time. But as m squared Rm increases, then the disruption to these bits between 0 and 1 are where it's shed part of the vortex, but kept part of the vortex. Until you get to here, this one is about 1.5. And after that, it's totally disrupted. So I would say it all hangs together, both for the shear layer and the big jet. Interestingly, big jet m squared Rm is more quite short. But again, it's an order one. These are all an order one estimate. But again, you get this nice picture that as you scan m squared Rm, you go from no disruption to disruption to destruction. And you can do the same for the isolated vortex problem. So here is actually, this is the disruption parameter as a function of time. On that previous one, it was taken at a time. Might have been better to have done a bit of time averaging, but they were taken at a time. This is what it looks like versus time. So this is disruption versus time for various plots and stuff, undisrupted, and then gets disrupted and settles, all goes all the way up to 1. And again, gosh, you probably can't see much that plot, because I can't. This again is m squared Rm versus delta. So there are some values down here which are undisrupted. Then there's this nice but quite steep, much steeper actually than in the shear flow one. Then there are these up here. Okay, you may or may not be able to see. So there's a sea of points here, which are ones that are disrupted to some extent. And then above this point, except this outlier, above this m squared on, everyone is disrupted. I can stop, but
I mean, I think you just really says you want to finish. It's there's some kind of questions on them still.
okay. So just the final thing is very quickly what we've been doing look at recently, which is, so this is going back to some advice at other flows, like these flows. What happens in these flows? Okay, so these are connected vortices. So you can have a sort of a row of vortices, and here it will matter whether I put the field in the X or Y. Here it will not. The key thing is that you get well. Let me explain what's going on. So this is a array of vortices, and the field is across. The field is in this one. The field is in the X direction. And now we know we're armed with theory. We know we should not really be looking for m. We should be considering what is m squared on it, right? So here m equals 0, so m squared on it is quite easy. Here m is 10 to the minus. What is it? 3. 10 to the minus. And Rm is 10 to the 4. So m squared Rm is still small here at minus 2. Interestingly, there is some dynamical effect. It's not disrupted the vortices really, but it has. It's not quite kinematic either. Here, m is 10 to the minus 2. So this is banging our m squared Rm order 1. And it does the job nicely. It disrupts the vortices. It doesn't destroy them, but it disrupts the vortices. A larger m, even though m squared Rm, well, yeah, here m squared Rm is large. M isn't large, but m squared Rm is large. So it's a complete the dynamic. If you do exactly the same flow, but with the field in the y direction, it's not nearly dramatic. Probably not that surprising in a way. But you could imagine if the field is in the y direction, it can sort of sneak by without being wound up all that much. You can sneak through the gaps, and you can see that here, it's almost kinematic. And even here, m squared Rm is order 1. it's not really expelled properly, and so it's not really destroyed. And if you take the Roberts cells are more, I showed the kinematics for the Roberts cell, so it's not quite clear what the dynamics of the Roberts cell is because of that, which I haven't worked out properly, you know, because if you remember the kinematic, it grew, went down, and grew again. Okay, so there's sort of two maxima here. You can see here that things are happening here at the saddle point. Okay, there is vortex disruption. I think it's a more complicated procedure than just out-and-out vortex function. Okay. Right. What could you do beyond this? So all I talked about today is the most straightforward thing you could think of: 2D incompressible MHD. Okay, there are lots of interesting extensions of it within the 2D world. You could look at more complicated array. Pat and Freddie Ramirez have done this with arrays that fluctuate. They find interesting results on when you get disruption or not. In terms of applications, you might say 2D is a bit, you know, astrophysical applications, you might say 2D is a bit restrictive. Now, there are 3D examples of flux expulsion, those convective cells I showed at the beginning. But one might imagine that you can get, that there are valid models which are quasi 2D. In particular, there is a nice model of so-called shallow water MHD, invented, discovered, derived by Peter Gilman in 2000. And there is a subtle question here of how MHD shallow water, like shallow water, does not, in its derivation, have any diffusion. Where diffusion here is crucial, right? How do you put diffusion with MHD shallow water? That of itself turns out to be a subtle question. The answer is in that paper. And you could do rapidly rotating shallow water MHD. You can achieve SW MHD in a nice set of equations, 2I by Zyklin and Luke Costello, the students with Stephen and me, has done some work in this. Physically, last one. Physically, there is one conclusion which really matters, which is that things happen when m squared Rm is orthogonal. So the difference, so anything that is hydrodynamic, there is a world of difference between hydrodynamic and weak field MHD. Because you only need a tiny bit of m squared to make m squared Rm huge. And so I would say the message is that one needs to be careful about hydrodynamic explanations of things astrophysical. For example, there are models of confinement of the solar tachocline, which involve hydrodynamic vortices to confinement. But there's magnetic field with no field, but there's magnetic field floating around in the sun for sure. And so m squared Rm is easy to get to m squared Rm. Argument here shows what bigger field you need to make m squared Rm or 1, in which case then you have the possibility of disruption of the vortices, and the whole theory then you have to wonder. So the overall message is that weak fields matter at higher Rm. It's a message that has been put forward in other contexts, particularly suppression of diffusion, suppression of the alpha effect. Based on mine. I'll stop there. Thank you.